This recording is a review of the stoichiometry in Chapter 12. Okay, we have to remember that a equation, we can consider it as a recipe. Okay, we consider an equation as a recipe. So this can be read for every 2 moles of hydrogen. We combine 1 mole of oxygen, it gives us 2 moles of water. It's a balanced equation. So this is our recipe. And in all the examples that we're going to do, we're going to look at the mole ratios. The mole ratio is just comparing, let's say, one reactant to the product, or maybe one reactant to the other reactant. Okay, we're looking at the ratios, and the ratio is always going to be in moles. So when we do conversions, we have to convert from the unit that we're given into moles, use the mole ratio, and then convert it from moles to the unit that the question asks for. So here we have the first example, and we go from moles to moles. Calculate the number of moles of water produced. Okay, so we're interested in water produced when we have 3.3 moles of copper nitrate when they are formed. So when we have a product, if we have 3.3 moles of copper nitrate, how many moles of water will be produced? Okay, so you can pause this and then hit play when you want to see the answer. Okay, so we know we have 3.3 moles of copper nitrate. Okay, and we're looking for moles of water. So our mole ratios, what we're looking for goes on top. So for every 4 moles of water produced, 3 moles of copper nitrate is also produced. And here's our mole ratio. So we start with our given. This is our given here. So we start with our given times the mole ratio. So we have 3.3 times 4 divided by 3 would be equal to 4.4 moles. So when we have 3.3 moles of copper nitrate produced, in this reaction we will have 4.4 moles of water produced. The next example, we go from moles to mass. So when we see mass, a little hint here is we're going to have to use the molar mass to convert the grams to moles and moles to grams. So we have our question here, how many grams of copper, so we're looking for grams of copper, would be needed to react with 2 moles of nitric acid. Okay, so you can put it on pause. Okay, so we'll look at how this is solved. Again, here is our equation. We're interested in grams of copper would be needed to react with moles of nitric acid. This is what we know. We have 2 moles of nitric acid, and we know 1 mole of copper is equal to 63.5 grams. Again, here grams of copper. We're interested in grams of copper, so we're going to need the molar mass. And here we have the molar mass. So we start with our given. We use the mole ratio. Here's our mole ratio for every 3 moles of copper that is used. We need 8 moles of nitric acid. So this is our mole ratio right here. And let me box it in. And here we use it here. If we stopped at this point right here, we just did the math here, we would have moles of copper. But the question asked for grams of copper. So we have to convert moles to grams. We know 1 mole of copper is equal to 63.5 grams. Again, we looked on the periodic table for the mass of copper. We do the math. 2 times 3 times 63.5 divided by 8, we get 47.6 grams of copper. Okay, the third example, now we're going from mass to mass. So we're given, okay, calculate the number of grams of carbon dioxide produced by the reaction of 29.5 grams of methane. So we're given grams here and grams here. So we're going to need to find the molar mass of methane, CH4, and the molar mass of carbon dioxide. And we're interested again in methane and carbon dioxide. So we look at our recipe, and we use the recipe to write down our mole ratio. So you can click on pause. So what we know, we have 29.5 grams of methane. 1 mole of methane, CH4, equals 16 grams. That means the mass of carbon, which is 12, plus 4 times the mass of hydrogen. 12 plus 4 is 16. And 1 mole of carbon dioxide is mass of carbon plus 2 times the mass of oxygen. That's how we get the 44. Mole ratio. We are interested in methane and carbon dioxide. So for every 1 mole of methane used, it produces 1 mole of carbon dioxide. And here's our mole ratio right here. So we start with our given. Given's in grams, and we have to convert to moles. So here we use the molar mass, and we got that from right over here. Okay, 1 mole of methane equals 16 grams. Okay, so we use that. Here's our mole ratio. Okay, and so we have that right here. And the next step, we convert moles of carbon dioxide to grams. Okay, so 1 mole of carbon dioxide is equal to 44 grams. If we just stopped here, our answer would be in moles moles of carbon dioxide. So we have to convert. So now we have it set up, and we just do the math. 29.5 times 1 times 1 times 44, divide by 16. And we get 81.1 grams. Okay, notice it's asking for a number of grams. This is the mass to mass. When we see mass, that's going to be grams. The fourth example we're going to be looking at is a volume to volume problem. How many liters, okay, liters of oxygen are required to react completely with 1.2 liters of hydrogen? Okay, so we're interested in hydrogen and oxygen. So we use our recipe for the mole ratio. And also, we have to remember 1 mole of any gas is equal to 22.4 liters. So we're going to use that to convert liters to moles and moles to liters. So you can hit pause and work it out. Okay, we're going to look at the answer. Again, we're interested in hydrogen and oxygen. We start with our given. Whoops, this should be moved over here. Mole ratio is 1 mole of oxygen to 2 moles of hydrogen. This should be moved over like that. Okay, here's the mole ratio. And again, we get that from our recipe. For every 2 moles of hydrogen, we need 1 mole of oxygen. We're looking for oxygen. Okay, how many liters of oxygen? And so that goes on top here. So we start with our given. We have 1.2 liters of hydrogen. We convert 1 mole to 22.4 liters. And so that would give us moles. Then we use our mole ratio. And then we convert moles back to liters. Again, the 22.4 It's going to cancel out. It's not going to do anything numerically. However, we would get the right units. And so we would divide 1.2 divided by 2. We get 0.6 liters. Moving on to limiting reactants. Remember, limiting reactant, we have two reactants, and we want to see which one we're going to run out of first. We say we have two different quantities, but we're going to maybe run out of one before the other. So we have to determine which one we're going to have in excess, which one is going to be the limiting reactant. So what is the limiting reagent when we have 49.84 grams of nitrogen and 15.7 grams of hydrogen? Okay, so we're interested in nitrogen and hydrogen. This is kind of two parts. You need to determine the number of moles of each one, and then pick one of them and see how much of one, if we use up one reactant, we can determine how much is required of that second reactant, and then compare. So you can put it on pause. So let's look at how this is solved. So we have 49.84 grams of nitrogen. 1 mole of nitrogen equals 28 grams. Okay, nitrogen is 14 grams times 2 is 28. Okay, so we look up, we have 49.84 grams, and we know 1 mole is 28 grams, so this is going to be greater than 1 mole. 1 mole, 49.84 grams is 1.78 grams of nitrogen. And the next one we have 15 grams of hydrogen. So here we have the 15 grams of hydrogen, H2, that's supposed to be small 2, subscript 2. So 15.7 divided by 2 is 7.85 moles of hydrogen. So what we have here, of the 49.84 grams of nitrogen, that is equal to 1.78 moles of nitrogen, and 15.7 grams of hydrogen is equal to 7.85 moles of hydrogen. So that's the first step. Okay, it's kind of the first step. We convert it to moles. The second step is we compare. We pick one of them. And in this case, I picked this one. I picked 1.7 moles of nitrogen. And I want to see when I use that up completely, when it goes, the reaction goes to completion, when I use this up, we want to see how many moles of hydrogen is required. So if we use 1.78 moles of nitrogen, we see, again, if we kind of look at nitrogen and hydrogen, for every 3 moles of hydrogen, we need 1 mole of nitrogen. So if we have 1.78 moles of nitrogen, we multiply times 3. This would be how much we would need, 5.34 moles of hydrogen. That's how much is required. And we look, we have 7.85 moles of hydrogen. So this is required, and this is what we have. So we have hydrogen is in excess. Hydrogen is in excess. And so therefore the nitrogen is the limiting reagent. We compare this with this. Okay, this is what we need, this is what we have. We have a lot more than we need, so this is going to be the limiting reagent. Okay, the next example, what is the maximum number of grams of pH3 that can be formed when we have 6.2 grams of phosphorus, Okay, 6.2 grams of phosphorus reacts with 4 grams of hydrogen to form pH 3. Okay, to form this. So we have 6.2 grams of this, 4 grams of this. And we can put it on pause. Okay, let's take a look at the answer. First thing we do is change it into moles. Okay, we have 6.2 grams of phosphorus. And we see here we have 6.2 grams of phosphorus, P4, and 1 mole of phosphorus, P4, is equal to 124 grams of P4. And that would give us 0.05 moles of P4. And we haven't let's just cover this up for now until we get to the answer. How we get that. Okay. Next one, we have 4 grams of hydrogen. Okay, we have 4 grams of hydrogen. And 1 mole of hydrogen is 2 grams, so we convert it to moles. So now we have 2 moles of hydrogen. So 6.2 grams of P4 would give us 0.05 moles. And 2 moles would give us, of hydrogen gives us, we have 2 moles of hydrogen. 4 grams gives us 2 moles. So we pick one of these. Okay, we pick one of these. And in this case, I pick this. Okay, so here I pick this one, 0.04 or 0.05. And we look at our ratio. For every 6 moles of hydrogen, we need 1 mole of P4, phosphorus. And so it would be 0.05 times 6 equals 0.30 the mole. And let's get a mole of hydrogen that is required. So if we use up all this, we need 0.3 moles of hydrogen. We have 2 moles of hydrogen. Okay, so we have 2 moles of hydrogen. So that's in excess. And so therefore, P4 is the limiting reagent. Okay, so from this step here, we see this is required, 0.3 moles of hydrogen is required, and we have 2 moles. So we have excess of that. This is the limiting reagent. Now we use the limiting reagent to find out, because we can't use this, we'll run out of phosphorus before we use all of this up. So we use the limiting reagent, that's right here. And we want to know how much product we have. For every 4 moles of pH3, we need 1 mole of P4. And that's the mole ratio here. Because now the second part, it's like 2 parts. And let's just kind of put a line in between here. It's like 2 parts. Above the blue line would be part 1 to determine the limiting reagent, and now we're in part 2. Here we use the limiting reagent, and now we're figuring out, we're trying to determine the product. And so for every 4 moles of pH3, we need 1 mole of P4. And then we convert that to grams. 1 mole of pH3 equals 34 grams. Again, phosphorus plus 3 hydrogens gives us 34 grams. So we do the math, 0.05 times 4 times 34 divided by 1. We get 6.8 grams of pH3. Okay, so that's the maximum number of grams that can be formed when we have these two. Okay, so we have to find out first the limiting reagent, then use that to see how much product we have. Okay, the last example we have is we're working on percent yield. We can consider this theoretical yield. Okay, we consider this a theoretical yield. If I use up all this, I should produce this. Okay, now percent yield. When we have 15 grams of Sp2S3 react with an excess of iron, we get 9.84 grams of antimony is produced. So we have this. We have enough iron, we have excess iron, so we don't have to really determine how much we need because we weren't given a value there. And then we produce antimony. So what is the percent yield of this reaction? First thing we have to do is use this, Sp2S3, this reagent, and to see if it's all used up, how much antimony it produced. We need to calculate the theoretical yield. Once we get the theoretical yield, we can use the actual yield. This is the actual yield. Okay, so you can put it on pause. Okay, first find the theoretical yield of antimony. Okay, so we are interested in, let me get rid of this dot here. Okay, so we are interested in antimony, which is this one here, and Sp2S3. So we have 15 grams of Sp2S3. We have to determine the molar mass, 2 times the mass of antimony plus 3 times the mass of sulfur. Okay, antimony sulfide. And that would be 340 grams. So we have only 15 grams. So 15 times 1 over 340. Here's our mole ratio. We get this for every 2 moles of antimony produced, we need 1 mole of antimony sulfide. So here's our mole ratio, and let me box it in red. Okay, and the next step is to, now we know how many moles of antimony we have, but we want to know how many grams. And so we convert moles to grams. We look up the molar mass of antimony, Sp, and that would be 122 grams. So now we do the math. 15 times 2 times 122 divided by 340, and we have 10.6 grams of antimony. This is our theoretical yield. Okay, this is our theoretical yield. Okay, and let me outline it in, let me underline it in the brown. Okay, that's our theoretical yield. However, we only produce 9.84 grams. We only produce 9.84, so this is our actual yield. Percent yield is actual yield divided by theoretical yield times 100%. So 9.84 divided by 10.76 times 100, it's a 91% yield. Okay, we did not recover all the antimony. For some reason, the reaction might not have gone to completion. We only got 91% of it. So this is percent yield. Okay, so this concludes the problem review for Chapter 12.